Okay. Um, so the most immediate news is my office hour. I have one office hour scheduled for this afternoon, and I have to do it by Zoom. So that link will be up on D2L. If you want to come to office hours today, it'll just have to be Zoom. Um, Let me know if that's a problem, and we can schedule something later this week. Um, and then maybe the most important news is exam 2 is on Monday. And the topics for that are everything up through particle kinetics. And remember, these are cumulative. All my tests and quizzes are cumulative, so you need to go back and be ready for stuff from the beginning, including the vector review, the math stuff. Okay. Um, does anybody have any questions on material related to the exam? Like I said last class, I think the way I would recommend getting ready for this is go back to the beginning problem and just go through all the daily problems. And you don't have to work them all. You probably don't have time for that. I mean, that would be the best, but I don't think anyone has time for that. So go back to the first one and read the question and ask yourself, do I know the steps to doing this, for doing this? And if you do, then keep going until you get to one you're a little more hazy on, and then spend a little time on that. You're just trying to get to the point where you understand the steps of how to do every problem and the reasons for those steps, like kind of at a level where you could explain to someone else how to do any one of these daily assigned problems. And if you get to that point, then if you get to that point and it's only 9:36 p.m. on Sunday night, then you can go to bed early. Okay. So remember where we are is rigid body kinetics. Um, and we're heading towards the main equations of motion for rigid body kinetics. That's Newton's second law and the moment equation, rotational Newton's second law. And before we could get into that, we had to define 1, 2, 3 things. The first one was centroids, which is our stand-in for center of mass. Those are the same thing as long as the body is homogeneous. Where do you need to use centroids in rigid body kinetics? I guess there's kind of 2 places. Well, 3 places if you if you consider the weight of an object. Yeah. Yeah, that's true. We will eventually get to those, but I guess I was thinking of specifically the equations of motion. So in Newton's second law, you need it because F net is equal to the mass times the acceleration of the center of mass. Okay, that was a bad question, but I'm going to tell you the answer to it. So you need to know where the center of mass is if you're going to be relating things to the acceleration of that point. Okay. And then second, in rotational Newton's second law, the moment equation, well, if you have a fixed point on your body, if your body is attached to the ground by a hinge or something, then you're in luck. You can use that as your about point, and you don't need to calculate the center of mass for that. But if you don't have a fixed point, then your about point has to be the center of mass. And so you have to find the location in order to do all your calculations for the about point. Okay. So centroids, then the second thing we have to define, well, we already did this. We're on the second thing, which is the mass moment of inertia about a point. Like, this is what you would call it if you like button your shirt all the way to the top and have a pocket protector and your glasses are, attached by tape in the middle. But if you want to be cool, then you just call it the moment of inertia. But either way, you have to remember all this other stuff. Okay. So if you want to seem like a cool guy, you gotta just call it moment of inertia. But either way, it's important that you remember that full meaning. And this is what we're talking about right now. You are here. And then after that, we have to talk about the moment of a force about a point. And again, if you're cool, you just call it a moment, but you have to remember that all this stuff matters. Okay, so we're talking about the mass moment of inertia about a point. Last time I gave you the definitions. Formulas, I guess. Formulas for the moment of inertia. So now you know I'm trying to be cool. The moment of inertia about the center of mass for 4 simple shapes. Those were a slender rod, a thin rectangular plate, a thin disc, and a sphere. Okay? But those are about the center of mass. Okay? So what if you want the moment of inertia about a point that's not the center of mass? And the answer is the parallel axis theorem. How many of you talked about parallel axis theorem in Physics 1? Okay. It's related to that. The parallel axis theorem is a thing. Well, I'll talk about what it is. Yeah, I think it's common that it doesn't come up, and you're just given, just like I gave you formulas for the moment of inertia about the center of mass, you can give formulas for moments of inertia rotating around different points, and you can kind of gloss over that in Physics 1. But here is the idea of the parallel axis theorem. If you have some arbitrary body, okay, and say that the center of mass is here, and say that you know the moment of inertia about an axis that goes through the center of mass. So I'm going to call this IC is the moment of inertia about an axis through the center of mass. And say that what you want is the moment of inertia about an axis that's parallel to that, but at some distance away. So say we want I sub A, which is the moment of inertia about a parallel axis at some distance d. Okay, so the distance between these two lines is d. Then the moment of inertia sub A is equal to the moment of inertia for the one that goes through the center of mass, plus the mass of the body times the distance squared. The distance between those two axes squared. So that's the parallel axis theorem right there. And it means that even though all I gave you was the formula, were the formulas for axes that go through the center of mass, we can easily calculate the moments of inertia for any other, for a parallel axis through any other point.
What happens when we derivate that? What's the derivative of inertia? I just trying to, thinking about the mathematical approach to why this works.
So yeah, why? So this comes from an integral definition, and yeah, you could go through. Don't write this down, but the moment of inertia about some point is the integral of over the whole mass of r squared dm. So for each infinitesimal little piece of mass, you have to figure out the distance from the axis to that point and square it, calculate that integral. And the way it works is, the definition of the center of mass is 1 over the total area times the integral over the whole mass. I guess, let me give instead of the centroid definition, I'll give the definition for the center of mass. So over the full mass of x, y, dm. And so this can't be area, this has to be mass total. Okay. And then you can, for each one of the little dm's in the definition of the moment of inertia, you can define that as a vector that goes from your A to the center of mass to the point you care about. That's just vector addition. And then you can go through this whole derivation and pull out the part of the integral that is the moment of inertia of the center of mass, and you come up with this formula. It's messy, a little bit long, but you can come up with this really clean solution by just using those two integral definitions. For the love of God, don't write that. Okay, so we have this. The one thing I want you to notice here this definition. Can MD squared ever be negative? Can mass ever be negative? No, distance is always positive anyways, and then you square it, so that has to be positive. So I want you to notice that in all cases, the smallest moment of inertia always goes through the center of mass. So it's always easier to get any body rotating about its center of mass than it is about any other point. Okay. All right, let's do a quick example. So let's say we have a rectangle. And first I'm going to do it with just kind of parameters in here. Then we'll put some numbers in. So let's say we have a height h and a width w. And we're doing a planar problem. The center of mass is right where the two axes of symmetry cross, lines of symmetry cross. So it's right here. And let's put a point A here. And we want to calculate the moment of inertia about A. Okay, well, this is our rectangular plate. We're doing a 2D problem, so all you have to do is think about, is this rotating like a blade or a paddle for the, let's look back at the rectangular plate. So is this rotating about X like a blade, or is it rotating like a paddle about Y or Z? So think of this as like,
I think it's going through like a blade.
like a blade, yeah. Think of that as like sheet metal that's spinning around in the plane, you know? And so, so we're going to use the mass moment of inertia formula that I gave you about X.
And if this was like a three-dimensional rectangle, would it be a paddle or more, would it still be a knife sort of thing?
Yeah, so if you think of this as thin, then it would be like, this would be like if you took a piece of sheet metal and we're like, hi-ya!
Or shorthand, like a or square shorthand.
The funny thing is, so I said thin rectangular plate here before. For this one, it doesn't matter mathematically whether it's thin or not. For the other two, it does. So this actually could be like a rectangular cylinder going as far as you want into the page. And this formula is still exact. But okay, so all that is just to say we're going to use this formula. The moment of inertia about the center of mass is equal to 1/12 m times the quantity L squared plus h squared. So the moment of inertia about C is equal to 1/12 times the mass of this thing times h squared plus w squared, using the parameters I have here. And then we're going to use the parallel axis theorem to find I sub A. Okay. So the distance is the distance from C, where our formula gives the moment of inertia, to A, where we want to calculate the point we want to calculate the moment of inertia about. Okay, so let's think of what the distance squared is. Well, I guess we could think of the distance. We're just going to use the Pythagorean theorem for this right triangle. Okay, so the distance is h over 2 squared plus w over 2 squared square root. So if you square that, d is equal to h over 2 squared plus w over 2 squared. And we can write that as h squared over 4 plus w squared over 4. And so I sub a is equal to 1/12 mass times the quantity h squared plus w squared plus, I'll write this as 1/4 of h squared plus w squared. So plus 1/4 times the mass times h squared plus w squared. Yes.
How did you get rid of the square root for d?
Because I wrote this wrong. This is d squared.
Oh.
Yeah, thank you. Because what we want in the parallel axis theorem is mass times d squared. And so now everything's the same except the coefficients. So if you get a common denominator, this is 3/12. 3/12 plus 1/12 is 4/12. So this is 1/3 times the mass times h squared plus w squared. Okay, so when would this come up? So let's say that we have an object like this. And let's say that the mass of this object is 10 kilograms. And this distance is 0.2 meters, and this distance is 0.6 meters. This plate has a fixed point at the upper right corner. So to use rotational Newton's second law, we want the moment of inertia about the fixed point, about that upper right corner. I'll call this point A so we can refer to that. Okay, so let's calculate it. Okay, so I guess I'm going to use the parallel axis theorem again because in general you're just going to have to use that, even though I just came up with a formula that we could just use for this. But so the moment of inertia about A is equal to 1/12 times the mass times the quantity 0.2 squared plus 0.6 squared plus the parallel axis theorem part, that is the mass times the distance squared. So 0.2 over 2 squared plus 0.6 over 2 squared. I need a calculator. So this is equal to 0.3 repeating plus 0.1 squared plus 0.3 squared. What's wrong with that? This is just 1.0. And so I sub A is equal to 1.3 repeating. And the units are kilogram meter squared. Okay. Any questions about that? And if your fixed point was somewhere else, then you just use that different distance from the center of mass to do this calculation. So now building a complicated shape out of simple shapes. Okay, so let's say that we have something like this. And we want to calculate the moment of inertia about some point A. How are we going to do this? Break it up into the simple shapes. So I'll have one rectangle here, and one here. Okay. So first calculate the moment of inertia of each simple shape about its center of mass. Second, use the parallel axis theorem to calculate the moment of inertia of each simple shape about A, and then third, just add those up. Okay, so let me do an example of that. So let's say we have an L shape, and the thickness everywhere is, let's call that 0.1 meters. And this is 0.1 meters. And this distance is 0.5 meters. And this distance is 1 meter. And let's calculate the moment of inertia about this point. Okay, so step one, we're going to break this up into two rectangles. So I'll call this one rectangle 1, this one rectangle 2. Okay, so for rectangle 1, the moment of inertia about the center of mass is equal to 1/12. Oh, I didn't give this a mass yet.
Yeah, it has to be a homogeneous density.
It does, and we're going to just always assume that. Yeah, so the mass is equal to 5 kilograms.
Because it's homogeneous, we can just break up the mass for the two bodies.
We can do it, yes, by the ratio of the areas. Okay, so this is equal to the mass of 1. We'll have to calculate that. Times the height squared, so 1 squared plus 0.1 squared. The total mass is 5 kilograms. So we're going to get M1 from the ratio of the areas. Okay, so the area of the first one is equal to 1 times 0.1. So 0.1 meters squared. The area of the second one is 0.5 times 0.1. So 0.05 meters squared. So the total area is 0.15. Yes.
That's not right.
Dang it.
You gotta like subtract area off that bottom left. So I did like 0.4, right?
Subtract.
Height or
Well, I did the I gave the distances so that
oh, you did?
yeah,
Oh, okay, sorry.
to make that easier, but I did forget as I was doing this that I was going to have to do this ratio of the areas. Was there another question or same thing? Okay. Okay, so now we got the total area. So now we can go M1 over the total mass of 5 is equal to area 1 over the total area. And so M1 is equal to 3.3 repeating. And I might as well do M2 here also. M2 over 5 is equal to 0.05 over 0.15. So M2 is equal to 1.6 repeating. Everyone with me on this? So you will have to actually do this on a few problems. Sorry, I kind of muddled the process for this, but so anyways, now we have the masses for each of those two rectangles, and now we can go back to calculating the moment of inertia. So the moment of inertia about the center of mass is 1/12 times 3.3 repeating times the quantity 1 squared plus 0.1 squared. And we get 0.28, I'll keep a bunch of significant figures, 0.56. Yes? This is about the center of mass of object 1. Yes, that's right. And now we'll go the moment of inertia about A for object 1 is 0.28056 plus the mass of object 1 times the distance from the center of mass of object 1 to our about point down in the corner. Okay, so what's that going to be? As a vertical distance, it's going to be 0.5 plus 0.1. So this is going to be 0.6 squared. As a horizontal distance, it's going to be 0.05 squared, just half of the width. And we get 1.4889 kilogram meter squared. So notice that in the total moment of inertia of that first simple rectangle, the contribution of the parallel axis theorem is much bigger than the contribution of the moment of inertia about its own center. Okay, and now we'll go to object 2, rectangle 2. So for this one, the moment of inertia about its own center is 1/12 times the mass of the second rectangle, 1.6 repeating, times the length squared plus the width squared And you get 0 point, oh, I didn't divide by 12 yet. Uh, 0.03611 kilogram meter squared. And now the moment of inertia of the second rectangle about that point A is 0.03611 plus the mass of the second rectangle times the distance from its center of mass to that corner, which is 0.25 squared plus 0.05 squared. And that is 0.11134 kilogram meter squared. Now add those two. And the total moment of inertia about A is 1.4889 plus 0.11134 which is about 1.60 kilogram meter squared. Any questions about that? Okay, so these distances, so this line here is our distance for rectangle 1, and this is our distance for rectangle 2. And you can just do both of those as, think of those as hypotenuses of right triangles.
So in that equation, if we go down like that, a little bit up. So the, like in parentheses, like 0.6 squared plus 0.05 squared, is that like the base and height of that triangle?
Exactly. Yep. And the reason, so this, what?
I said this looked negative, but he just put that in there.
Oh, yeah. So since you're squaring it, you can do it as vectors and have negatives in there and they'll disappear. But if you just look at this green right triangle, the vertical leg is 0.5 to get to the bottom of the vertical rectangle, and then another 0.1 to get down to the corner. So that's where that 0.6 comes from. And the thickness of this is 0.1, so that horizontal leg is 0.05.
So in those IC equations, in that parentheses, the I squared plus 0.1 squared, is that the base and the height of the rectangle itself?
This here?
Yeah.
That is the height and the width of the rectangle itself, and that comes from the formula 1/12 m times L squared plus H squared. Any other questions about that right now? So in problems that are trying to make it a little simpler for you, they would actually tell you what the masses are of these individual small rectangles, and then you wouldn't have to do that ratio thing. Okay, so remember, all of this is getting towards using the equations of motion for rigid body kinetics, which are Newton's second law and rotational Newton's second law. And before getting to that, we had to do center of mass. We had to define that, and we did. And we have to define the moment of inertia about an axis, and we did. And now we have to define the moment of a force about a point. And we'll just call these moments, but remember that the force matters and the about point matters. And I should say, physicists call these torques. So here's me like eye rolling at physicists and their endless nonsense. Because in D form, a torque means either a moment or a couple. I guess it always means a couple even, acting along an axis of a beam. So we have that name already reserved for something specific.
Did you say these requirements are for Newton's second law and rotational?
Yeah, rotational Newton's second law is the moment equation, or the torque equals I alpha equation from physics 1. Okay, so here's the definition of a moment of a force about a point. So there's the body. And let's say that, at some point, I'll call this P. There's a force vector applied to this body. And we want to calculate the moment about some given point A. So what's the moment MA produced by the force F about the point A. That's what we want to calculate. So the first thing we're going to do is define a new vector. And that vector goes from A to P. So that red thing is this new vector we're going to define, and we're going to call it rho, the Greek letter rho. And you can always calculate it as the coordinates of P minus the coordinates of A. And then with that definition, the moment of the force, and I'm going to write this as a vector. A moment is a vector. We'll see, to us it sort of looks like a scalar, but it is a vector, is equal to that rho vector that we just defined crossed with the force vector. And when I do these with a rigid body, I'll always enter these in a table form. This is the same table that you saw in statics, the people who took statics from me. So my table will always have a column for rho. And you can always calculate this as P minus A. It'll have a column for the force vector and then a column for the moment. And each row of this table will represent one load acting on the body. We're only going to do these calculations for problems in the XY plane. So we're only going to use the moment equation, which I'm always going to call rotational Newton's second law, for problems in the XY plane. So we can treat, we can treat the vector moment as a scalar, as a single number. But remember that it always is a z component because we're always going to be taking the cross product of two things in the xy plane. Okay, so let me show you, like, for example, if we have a table entry, row, force, moment, and the force we're dealing with, let's say it's this force F12. And let's say the row vector is 5, -3, 0. And the force vector is 400, -800, 0. If you take that cross product, you get 0, 0, -2800. Well, you can just think of that as, so let me write it in sort of a simplified form where we have row, force, moment, our row vector we could think of as just 5, -3. Our force vector we could think of as just 400, -800. Our cross product is this times this minus this times this, and you get -2800. Okay. Just remember that that's really a z component of a vector. So that's really a z component of a vector. Okay. Let me do an example. So let's say that we have a body like this. And let's say that this length is 0.5 meters. And this length is 0.8 meters. And let's say we have a force vector at the center acting down. Let's say that this is 50 newtons. And let's say we have an unknown force vector. I'll just call it R, acting here. And let's say that we want to calculate the moment about this point A. So what's the total moment about A? I'm going to write out my table. So I have row vector, force vector, and the moment. And I'm just going to go through these forces one by one. First, I'll do the 50 Newton force. The row vector is the vector that goes from where the force is applied. From your about point to where the force is applied. It's the point where the force is applied minus the coordinates of A. So this row vector is this. So the x component of that red vector I just erased is 0.25. It's on the video. The y component of that vector is 0.4. Everyone with me on that row vector? The force vector is 0, negative 50. The cross product is this times this minus this times this. So we get negative 12.5. And now we'll do it for the r vector. So the vector from the about point to where that r vector is applied. So the vector we want is this. So the components of that vector are 0.5, 0. The force vector is some r unknown rx and some r unknown ry. The cross product is this times this minus this times this. And so that is 0.5 ry. And so the total moment about A is negative 12.5 plus 0.5 ry in the z direction. Or you could write it as 0, 0, negative 12.5 plus 0.5 ry. Any questions about that? Okay, so you can see from the way moments are calculated, they change if the force changes, and they change if that about point changes, right? Both of those come into the calculation, so changing either one of them would change your answer. There's one case where a moment does not change based on the about point. So one weird type of moment that doesn't depend on the about point. Anyone know what I'm going to talk about here? Couple, exactly. Okay, so a couple is an equal and opposite pair of forces acting at a distance. Okay, so let me show you an example of this. So I could call this P1 and this P2. And at P1, let's call this the force vector F acting there. And then at P2, we have to have an equal and opposite force. So it has to be parallel but going the other way. So this is negative F. Okay. And let's calculate the moment about some point A. Okay. So what's the total moment about A for this couple? So what I'm going to do is I'm just going to calculate the moment produced by F, the moment produced by negative F. Both of those are going to have A in them because moments depend on A. But then I'm going to multiply out everything I have, do cancellations, and what we're going to see is A disappears from the equation. Okay? And the meaning of that is no matter what A I chose, the moment produced by this couple would be the same. Okay? So the total moment for this couple, we have our row vector for F. So let me start out by saying, okay, we have row 1 crossed with F plus row 2 crossed with negative F. And now I'll substitute in the meaning of this row vector. So we have P1 minus A all crossed with F plus P2 minus A all crossed with F. So I just used the definition of row vectors. And now we can distribute this cross product through those parentheses. So this becomes P1 cross F plus negative A cross F plus P2 cross, and this should have been negative F. So P2 cross negative F minus or plus negative A cross negative F. And now I can pull out all the negatives. So we have P1 cross F minus A cross F minus P2 cross F. Double negative says this is plus A cross F. And you can see that these two cancel. And the moment produced by this couple then is just, if I redistribute, P1 minus P2 quantity crossed with F. So it has no dependence on where the about point is. So in that sense, we're going to just think of this as a pure moment. And in the table, you'll put this in like this. If you have like a couple that we'll call M, and you have your table with your row column, your F column, and your moment column. We don't care about the row vector because that's only there to get A into the equation. We don't care about the F column because these are equal and opposite forces that cancel each other out. So you can forget about all this and just put it in as M or whatever the value is. Okay, let me do one more example. So let's say we have a beam like this with 100 Newton force down from the center. And let's say at this corner, we have an unknown force vector R and an unknown couple M. And let's give these dimensions of, let's say this is 2 meters long and 0.3 meters tall. What's the total moment about the lower left corner? Okay, so I'm going to write out this table. So rho, force, moment. I'll start with that 100 Newton force. The rho vector is this. It goes from the about point to where the force is applied. So the horizontal component is 1 meter. The vertical component is 0.15 meters. So we have 1, 0.15. for the row vector. The force vector is 0, negative 100. The cross product is negative 100. Then we have the force vector, r. That's acting at the about point. So what's the vector from the about point to where that force is applied?
0.
Yep, 0, 0. The force is Rx, Ry. So the cross product is 0. And then the moment, we don't care about a row vector. We don't care about the force. And this is just m. So the total moment about that lower left corner is negative 100 plus 0 plus m, negative 100 plus m about the z-axis, or in the z direction, I mean. Any questions about that? The other thing about this table is we've kept track of all the forces as we've gone too. So what about the total forces acting on this body? Well, those we can get from just adding up these force vectors. So the total force on the body is 0, negative 100 plus Rx, Ry. So that's Rx, Ry minus 100. And these will both be useful things for us. Yes?
So would we be given that moment value?
Usually, well, sometimes we'll be given it, sometimes we'll have to calculate it. We can't calculate it just with this, but now when we go to the moment equation that says this sum of moments is equal to the moment of inertia times the angular acceleration, you know, if we're given something that lets us determine the angular acceleration, then we can back calculate that couple. So all of this is just heading towards using Newton's second law and the moment equation. Any other questions?
Was the reason why we have to do m here in this last example because of the unknown force vector?
No, it's actually, in this case, the, so things can provide couples. So imagine that this beam is really connected by a little bit of material to the wall.
Yeah.
Okay, so this is welded to the wall. And that weld will do two different things, or three if you want to think about it that way. It'll prevent it from translating horizontally. That's the unknown X force.
Yep.
It'll prevent it from translating up and down. That's the Y force. But it'll also, you know, a hinge joint could do that. A hinge joint would keep that part of the metal right there. But a hinge joint would let it fall down. Okay? This weld joint doesn't let it fall down. And the way it does that is it applies a series of couples to this where, so this thing wants to fall down. This has to apply a force this way with a corresponding force this way. And that's the unknown couple.
Okay. So that's the reason as to why we have m.
That's why that would appear in a real problem, yeah.
Okay.
Or, you know, there could be cases where that's the shaft of a motor, you know, and you want to figure out what couple that motor has to apply to the body in order to get a certain kind of motion, a certain angular acceleration. So we would go to the moment equation, put in the angular acceleration we want, and back calculate that couple that the motor needs to provide. And then we'd know what strength the motor, what voltage we have to, you know, send to the motor, that kind of stuff. Yeah, we'll go into all this. You don't have to, this doesn't all have to be crystal clear yet. But whenever you're confused about what a moment is or how to use this table, just remember to go back to these notes. Everything you need to know about moments is basically in today's lecture. Okay, that is all.